Hello and welcome back. So far we have understood how to build a multiple linear regression model. We have taken a data set, we split it into train and test, we kept the test set aside, and then we took the train set and did exploratory data analysis, did feature engineering, converted our categorical columns to numbers, then passed it to a machine learning model. Here it is a linear regression model, and then we trained the model and tested it with the train set and calculated the accuracy scores, R square score and the RMSE score. And we found that the model is not working well, right? If you look at the code again, the model is giving only 62% accuracy there. I said that's underfitting problem. In general, when the model is underfitting, we will never touch the train test set and try to test it and validate it. But here, in our previous example, we have actually applied, we passed our test set X values and then predicted the test set Y values, test predict, and then we tested it with, we actually compared it with the test set's Y values, original observed values, and then calculated accuracy. The R square score we have got was 66%, right? So I did not expect any miracles there, but just tested it, what's happening there, right? So we have got 66% accuracy. So the model is not working well. The model is not working well. For sure we can say that, right? So in this case, that we may have to improve the model's performance. And before we improving the model's performance, right, we try to check whether the problem is with the data or the algorithm. Right? With the learning curve, we understood that till 400 records, the model has learned something. But beyond 400 records, it did not learn anything, right? The test accuracy and train accuracy were kind of same there. That means the algorithm is failed in understanding the data patterns, right? In the complexity in the data, the data's complexity, the algorithm failed to understand. So in this case, we may have to improve the algorithm's complexity, or we may have to apply another algorithm which is more complex. So before we apply another algorithm which is more complex, we need to understand the concepts of underfitting and overfitting. When underfitting happens, when overfitting happens, how to fix that. So let us, that's also called as bias variance trade-off. So let us try to understand the concept with some diagrams initially, and then we'll go and look into the theory behind that. Okay. So if you look at this diagram, the complexity in the data is a little curvy, right? It's a little polynomial. But the model we fitted is kind of straight line. The model is unable to understand the pattern inside the data, or when you try to calculate the accuracy, right? If you try to, let me take a screenshot of this. If you try to understand calculate the accuracy of this model, that the predicted values are going to be like this: here, 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 and here, and here, and here. So the difference between the actual value and the predicted value is the error. So when each error is adding a little, each prediction is adding a little bit of error, the error is more and R square score is less. Okay, that is one thing. So that's where the underfitted model we have got. The train set, on train set, the model is not able to understand because the pattern is non-linear, not exactly this kind of a pattern in our data set, but in general I am trying to explain. The pattern is non-linear and the model is is a straight line, and the error is high on the train set. It is called as underfitted model. When model is underfitted, there is no hope that it will work on test set and production. So we generally strive to improve the performance of the model on train set. When it is working good on train set, that's when we look into the test set and try to calculate accuracy or whatever, right? So the problem with this model, right, with this straight line, is that the line is going even further, right? It's a straight line, it is going even further, but your test set data may come like that, right? In that case, your error is going to be even higher, right? In our particular data set, right, the test set would have came like this, maybe like that. So that's where we have got 66% accuracy on the test set and 62% on the train set. Ultimately, the model did not understand the pattern. So what we have to do is we may have to make the model a bit complex. Or if you add a polynomial term, the x square term, the line becomes a curve like this. Right? When the line becomes a curve, the predicted values are going to overlap the actual values most of the places. But here it is not. Right? Most of the places it will overlap the actual values, and you will get a less error. Right? This is the only error you get, or maybe little bit of error here and there, and on train set you will get good accuracy. When the train set is giving good accuracy, the algorithm is giving good accuracy on train set, there is a hope that it will work on test set. Suppose that your test set data is like this, right? If the line goes like that, right, it's going to work well on the test set also. This is called a just right model or the best fit model. Okay, so the next step we need to do, so far we have built a model and looked at the accuracy, and the accuracy is not good. The next step we need to do is we need to find out the best model which actually understands the pattern well, at least on the train set. Once it works on train set, then we'll think about the rest of the things, right? So in the process of improving the accuracy, we may add second degree polynomial and third degree and fourth degree also. When we add too many degrees of polynomials or too many higher degree terms in the polynomial, the model may become overfitted. When I say overfitted, if you see this higher degree polynomial is actually striving to touch each data point there, forgetting about the generalization. What is generalization? The model should work well on the train set and test set both, and production ultimately, right? So when you added too many complex terms in the model or to the equation, it actually is trying to touch each data point there and make the model work best on the train set, forgetting the generalization. When it forgets the generalization, right, your test set data may come like that. So for first two records it may have predicted properly, but the next records the error is so high. For the next record the predicted value is going to be somewhere here, predicted value is going to be somewhere here, predicted value is going to be somewhere here, right? The error, the distance, see, a lot of distance is there. That means on the test set the error is going to be high. So in the process of improving model's accuracy, if you add too many polynomials, too many polynomial terms, the model may become overfitted. Okay, the model may become overfitted. So we need to be careful or select the best model. We'll see how to select the best model in next session, but here we'll try to understand more about bias variance trade-off. When it will happen, when underfitting will happen, when overfitting will happen, how to fix them. So let us try to understand that. So we understood that we start with linear regression and try to make the model a bit complex and that whole process. But when this underfitting will happen, or underfitting is called as high bias also. The overfitting is called as high variance. So when model is not working well on the train set, we say it is underfitted, or the model is too simple to learn the underlying structure of the data. If you look at the previous diagram, right, this is simple algorithm and data's pattern is a bit complex, right? The algorithm was unable to, the model was unable to understand the complexity, underlying complexity in the data. So that's when the underfitting will happen. How to fix underfitting? Select more powerful model. If you look at this diagram, it's a simple data set. Only one X is there, right? If you have to make the model a bit complex, right, you need to add higher degree polynomials. If I add second degree polynomial, it actually worked well. Third degree and fourth degree, it actually kind of worked well on the train set, but may not work well on the test set. So you make the model more powerful by adding, you make the linear regression model more powerful by adding additional polynomial terms. That is called as polynomial regression. We'll see that in coming session. But that's called as polynomial regression, and the model is we are making the model more complex to understand the underlying patterns well. Okay. The second way you can actually improve the performance or make the model work on train set well is better, finding better features. feeding better features to the learning algorithm. How can you feed better features? Maybe you can find new features from the business. You can ask the business analyst to give more new features which are more relevant to the target variable, or the data, the pre-processing we have done may not be appropriate. That's when the relationship between the input variables and the output variables would not have that strong, right? The input variables and output variables are not strongly related, then also the underfitting will happen. So the feature engineering may be a problem. The finding better features, new features may be a problem, right? And then feature engineering may also be a problem. So we need to go back and revisit our feature engineering, and we may have to do some more analysis, statistical data analysis, and try to improve the model's accuracy. Okay. The third way is reducing constraints on the model. Reducing constraints will come in regularization or hyperparametric tuning. The concept called as regularization in hyperparametric tuning. That comes in coming sessions. We'll explain. So for now, right, when you reduce the regularization hyperparameter term, the magnitude of the hyperparameter term, model becomes complex. That way you can actually fix the underfitting problem or high bias problem. Coming to overfitting, model is too complex relative to the amount of noise in the train set. So here, if you look at this graph, right, there is some noise in the data, right? Maybe some data points are a bit away from the regular pattern in the data, and our algorithm is trying to catch hold of that. Let me go back to the diagram there. Right? If you have a data point somewhere here and maybe here, if you are trying to build a more complex model, right, it may be actually trying to go up, right? It actually started somewhere here and it is going up and trying to touch those data points and come back, and then again it's going like it's actually trying to do that. It is actually trying to touch all the training records, or it is trying to give maximum accuracy on the training records. In that process, it may actually ignore to generalize. In that case, you will get good accuracy on the train set, but on test set it may fail. It may fail to give good accuracy. So that is called as overfitting. When you actually make the model too complex, it may try to catch hold of the noise, underlying noise in the data set. So that's a overfitting problem. How to fix it? Simplify the model by increasing the constraint. Regularization concept here. We'll come to that later. Right? If you increase the regularization term, right, the coefficient of the regularization term, the coefficients of the equation will reduce or come down to zero, some of the coefficients, and that way the model's accuracy, the model's complexity reduces. We'll see this in a coming session. But the other ways of fixing the overfitting problem is gather more training data. In our current data set, there is no problem of data because by 400 records it understood the pattern. If you look at the learning curve, right, learning curve is very useful in understanding whether the problem is with the data or the algorithm. When you did the learning curve, by 400 records it understood whatever it need to. That means the second way of fixing the problem, the overfitting problem, anyway the problem is underfitting here, right? If the overfitting is happening, the second condition is not going to work here. Okay, and reduce the noise in the training set. If I have shown you that here in the diagram, if there are some outliers or the data points which are off the track of the other data points, we may remove those records and then try to build a model, and that may actually fix the overfitting problem. So overall, the underfitting is called as high bias, the overfitting is called as high variance, and then to fix underfitting, you may have to make the model a little more complex, or find better features, or look at the feature engineering and try to change the way you did feature engineering and see if the model performance improves or not. Coming to overfitting, it is high variance, and then simply the regularization, right? Simplifying the regularization coefficient may improve the accuracy or may reduce the complexity in the model, and overfitting is happening because of more complex model. Complex is too, the model is too complex. Okay, so gather more data. Sometimes it is not, it is needed. When you do the learning curve, the model is still learning even after you have passed all your data. If the model is still learning, that means the training error and test error are still converging. In our case, they actually became parallel. After 400 records, they became parallel. But in some cases, what happens is they'll still be converging. That means data is not sufficient. Then you may have to collect the data. Okay, reducing noise, unnecessary records or outliers. If you take out, then the model will work well. The model will work well, or the algorithm will not try to capture the pattern of the noisy records. That way, it will be aligned with the train set and test set. So these are the points on high variance, high bias, and high variance. And three more points are there. The bias, the part of the generalization error is due to wrong assumptions, such as assuming that a linear pattern is there in the data when the data is quadratic. Okay, and variance, this part is due to excessive sensitivity to small variations in the training data, or having outliers, or the model trying to fit the outliers well and forgetting the generalization. Irreducible error, in every data set there will be noise, a little bit of noise, right? So we can clean up the data and do more feature engineering, or the statistical data analysis to understand the error. If we can reduce, we will reduce it. If not, we can leave it. Still the models will work well. Okay, so increasing model's complexity will typically increase its variance, or makes the model overfitted, or reduces the bias. When the model is overfitted, it is the underfitting reduces. When the model is underfitted, overfitting reduces. Or if the model is having high variance, it's going to be low bias. When the model is high bias, the variance is going to be low. That's called as bias variance trade-off. When you are trying to fine tune a model, or trying to increase the complexity of a model, you will actually encounter this, right? When variance increases, bias reduces. When bias increases, variance reduces. This is called as bias variance trade-off. Thank you.